These are the notes for section 10.1. We're going to look at sets, some terminology, counting, and Venn diagrams. So first, a little bit of vocabulary when we think about notation for sets. And the way that we're going to define set is as a well-defined collection of objects. And so usually we represent these when they're numbers in curly brackets. So the example of 1, 2, 3, 9, and 12. We also use some other type of symbols when we think about a set that contains no elements. Sometimes we show that as a bracket with literally no elements in it, but another way that we can do that is we can use that circle slash notation. So what looks like a letter O with a slash through it, indicative of empty set, or sometimes known as the null set. When we represent sets that have the exact same elements, we can use the equal sign in between them, so set A equals set B. When I have a situation where every element of A is in B, this kind of sideways U with a line below it, we refer to that as an improper subset. If we grab up a group of items from the set that doesn't include all the items, then that is known as a subset. And so when we have a subset of B where A is not equal to B, that's this sideways U symbol, that is a proper subset. So in our example, if we have set that contains A, B, and C, it asks us to name all the elements of the set and then list all of the subsets and which ones are proper. So go ahead and pause the video, give that a try, and come back and check your work. So take a look at what you have. So the set ABC, ABC is a subset of ABC, an improper subset. We also can take just A, just B, just C. We can take A and B, we can take A and C, we can take B and C, and then the empty set. So a total of 1, 2, 3, 4, 5, 6, 7, 8 subsets. And that's actually a rule. If there are n elements in a set, then the set has 2 to the n power subsets. So 1, 2, 3 elements, 2 to the third equals 8. So as an example, EFGH has 2 to the fourth power, which is 16 subsets. When we have two sets together, sometimes we're concerned about all the items that are in each set. Sometimes we're only concerned about items that are in one or the other. And sometimes we're concerned about the items that are in both. And so the intersection, elements that are in both set A and set B, we use this kind of upside down U to represent that. And then the right side up U is the union, elements in A or B. So as some examples, given A is 1, 3, 5, and 8, B is 3, 5, 7, C is 2, 4, 6, 8, we're asked to find the intersection of A and B, the union of A and C, the intersection of B with the union of A and C, and the intersection of A and B intersected with C. Go ahead and pause the video, work through these problems, and then you can check your work. So taking a look at these sets of instructions, A equals 1, 3, 5, and 8. Set B is 3, 5, and 7. Set C is 2, 4, 6, and 8. So A intersection with B. So those are the items that are in both A and B. And you can see that A contains 3 and 5. B also contains 3 and 5. So that would be the intersection of those two sets. 1, 8, and 7 are in one or the other, but not in both. The union of A and C. Now we want all the items that are in A and all the items in C. So 1, 2, 3, 4, 5, and 6. And then 8 exists in both. So the intersection of the two would contain 1, 2, 3, 4, 5, 6, and 8. The intersection of B with the union of A and C. So now we're asking ourselves, what items are in B that are also in this union? So 3 and 5 were part of B and they're also part of this union. And the intersection of A and B, which intersects with C, well, intersection of A and B was 3 and 5. None of those exist in C, so there is no intersection there, so that's our empty set. We also think about the complement of a set, and we use a symbol with a straight line above the set name, which means the elements that are not in that set. So the complement of A would be the items that are not in A. So if we're given this what's called a universal set, these are all the numbers that we're considering. If A is 1, 3, 5, 7, and 9, then the complement of A would be those items that are in our universal set that are not in A. So 1, 3, 5, 7, 9, all the odd numbers. So our complement would be 2, 4, 6, and 8. Let's take a look here. So the union of not A and B. So not A is 2, 4, 6, and 8. B is 1, 3, and 5. So now we have 1, 2, 3, 4, 5, 6, and 8. The only item that's not there is 7. So we're asked for the complement of the complement of A with B. So these are the items that are the universal set that are not in this group. So our complement of A, 2, 4, 6, and 8. Our B is 1, 3, and 5. So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6, and 8. So the items that are there are 7 and 9. Those are the items that are in the universal set that are not contained here. Okay, let's move on. We're going to take a look at Venn diagrams as it relates to sets. So you're familiar with the concept, Venn diagram of overlapping circles. So if the entire circle exists inside another circle, then A would be a subset of B. If there's no overlap whatsoever, we have the empty set, which are known as disjoint sets. When there is an overlap, that overlapping area is what we refer to as the intersection. The union, which is all the items that are in either A or B, so that would have them both darkened, the union of A and B. And then here we have the idea of the universal set. Here's A. Everything that's in the universal set that's not in A would be the complement of A. So we can use these sometimes to do counting. So n is the number of elements in A. So if we have the number of elements in the union of A and B, that's the number of elements in A plus the elements in B, but then we subtract off the duplicates, the ones that are the intersection of A and B. We don't want to count those twice. So let's practice a few. So we're given a generic Venn diagram, which is some X's marking items that are in set A and set B, and then here's our intersection. So the number of items in set A, 1, 2, 3, 4, there's 5 of those. So n of A is 5. Here we're asked to find the number of items that are in the union of A and B. So remember what that is. The union of A and B is going to be equal to number of items just in A plus number of items just in B, but we're going to subtract off the number of items that are in the intersection of A and B. So in A, we have 1, 2, 3, 4, 5 of those. In B, 1, 2, 3, 4, 5, 6 of those. But then we have to subtract off these that are contained in both, which is 2. So 5 plus 6 minus 2, that's 9. So the number of items that are in the union of set A and set B is 9. And if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9 items altogether. Okay. We're not always able to count individually. Sometimes we're given numbers for this purpose, and then we can use these formulas to be able to determine that. So our counting formula, we have 100 college students, 35 in college algebra, 52 in computer science, and 18 in both courses. So this says how many were registered in college algebra or computer science. So let's think about what that or is. Okay. and would indicate intersection, college algebra and computer science, or would be either. So this is saying how many were registered in either college algebra or computer science, but keeping in mind that we have some that are duplicates that are registered in both courses. So let's think about what that looks like. The number of items that are in college algebra or computer science. So it's a union. A union B equals the number who are in A, college algebra, plus the number in computer science. But then we're going to subtract off the number that are in the overlap. So let's take a look at that. The number who are in college algebra, 35. The number who are in computer science, 52, but we're going to subtract off the overlap, 18. So 35 and 52, that's 87 minus 18. So these are the number of students who are in college algebra or computer science. Now we're asked to do that using a Venn diagram. So let's take a look at what we have here. 18 registered in both courses. So that's our overlap. Here, the entire amount was shown, this amount outside the overlap. So B contained 6 with an overlap of 2. A contained 5 with an overlap of 2. So these items that are just sitting out here in A was the number in college algebra minus our overlap. So 35, 52. If we were asked how many are just in college algebra, but not in computer science. Okay? So there's 35 altogether in college algebra, but 18 of those are also in computer science. So 35 minus 18 is going to equal 17. And how many in neither course? Well, how many students did we survey altogether? 100. 35 are in college algebra, 52 in computer science, but 18 were both. So we don't want to double count them. We're talking about 69 students altogether, so 100 minus 69 gives us 31 students. So that's a little bit of a walkthrough about how we can use counting formula, both algebraically, mathematically, and then visually with the Venn diagram. So go ahead and complete your summary on this page. And be sure to check the instructions on Canvas to see if there's anything else that you'll need to do. And we will do the practice set for these problems next time we get together.